Welcome to the 2022 HLS Solutions Conference, Session 4, Hydrology and Sustainability. My name is Francisco Barrios from Terra Group International, and I'll be your session chair. I would like to take this moment to thank all the people that make this conference a success, from C3 Alliance to the speakers, the volunteers, the sponsors, everybody. So thank you. Quick update. Commodity prices up. Gold 1650, silver 18.6, copper 3.5, nickel 9.8 a pound, crude oil down $85 a barrel. So today we have an amazing lineup of speakers, and I hope that you enjoy and expand your knowledge on the different subjects that we'll be touching in this session. With that, please join me in welcoming Mr. Mark Smith. Mark Smith is a Chief Advisor and Geotechnical Engineer for Pito Associates, and he will be presenting liquefaction in heap leach piles.
Thank you for that. Can I turn the, do I need to be up there? That makes me nervous. There, that's better. And I'm already nervous because he told me if I push this button, the conference ends early. So, so I'm going to talk about nobody's favorite topic, but I promise to keep it very high level. And my goal here is to give you some idea what it is and why it might be important to you, and to give some basic screening tools to decide if your project might have this problem. So first off, what is it? Oh, first, thanks to my partner in crime, co-author, because he did all of the really heavy lifting, most of the paper writing, most of the presentation preparation. So my one task in this whole thing is to make the presentation. So thank you, Dr. Sinha. So what is liquefaction? Well, the name is all of it. Most of us in here know the old Westerns where the innocent victim steps into it and the earth swallows her up. Well, that doesn't really happen, but that is liquefied sand. That's caused by upflowing groundwater, creating a partial fluidized bed. That's not the kind of problem we ever have, but the mechanics are very similar. What we have is a problem. What we can have is a problem where you've got a relatively loose material, and I'm going to call it soil because this is soil mechanics, but spent ore or it's tailings, but it's in a looser state so that when you load it, it compresses, or what we call for liquefaction purposes, contracts. It's a contractive material. And if it's saturated or nearly saturated, it tries to push the water out of the way. And if the permeability is low enough, the water can't get out of the way, pressurize the water. The shear strength of a soil is the overburden effective stress, or the confining effective stress times the tangent of the friction angle. The effective stress is the total stress minus the pore pressure. So as you pressurize the water, your shear strength goes down. And if you pressurize it enough, your shear strength goes to zero, and that poor sweet mom in the Western gets swallowed by earth. So we don't actually see full liquefaction like that very often. In most circumstances, we see some sort of cyclic mobility, partial loss of shear strength, but it's in the spectrum of liquefaction. It's the same mechanics, just not fully fluidized. Now, one interesting part of this phenomena is if you have a loose sand, so the grains are kind of separated, and you load it, either just normal load or shear load from an earthquake, the particles will come closer together, or they'll compact on each other, so it gets smaller, it contracts, and that's what creates the water pressure. But if it's dense and you shear it, they'll actually roll up and it dilates, it gets bigger. And that's pretty counterintuitive. You load material, this is principally shear loading, but you load material with, say, an earthquake or blasting or whatever, and if it's already dense, it's going to become less dense. So that's what this graph represents. The middle graph, geotechnical engineers use void ratio. That's just kind of a different way to state porosity. So most people in here are probably more familiar with porosity. They are equatable by a very simple equation. So if it's loose sand and you load it, it's gonna decrease its porosity to a certain point. And if it's dense sand or tailings and load it, it's going to increase the porosity, but they're going to come to the same point eventually. If they're identical materials except density, they will arrive at the same point. And that point is a point on the critical state line. And the critical state line is interesting because now you told me the laser, but I've already forgotten it because I was so worried about the doomsday thing. Oh, thank you very much. So the cool thing about the critical state line is once you've established that, whatever your stress state is in the field, whether it's up here somewhere or down here, if you load it, it will move towards that critical state line. And it can't cross that line. That's kind of, we call it critical state. It can't cross that line. Instead of crossing that line, it fails. Your system has a problem. So that's tiny insight into critical state soil mechanics. But that's what causes liquefaction. So you need relatively loose material. You need relatively high saturation, not 100%. That's a common misperception, but it needs to be reasonably high. And you need a load applied, some sort of differential load. And I promised a screening tool, and I'll dabble these in during the lecture. So one is every soil mechanics lab in the world does Atterberg limit tests. And the most common Atterberg limit is liquid limit. This is the moisture content at which your material makes the transition from mostly solid to mostly not solid. And if your ore is anywhere near that moisture content, you need to do a lot more work on your project or figure out how to operate the heap so you're not up there. You don't want to be anywhere near liquid limit. Now, I do like that Krishna decided liquid should have 2 eyes. So I think that's a very nice twist. We could trademark that. There's kind of a next level. You can go get a little more sophisticated, but I think in general, you kind of look at this, and I do that a lot. I look at plastic index and liquid limit a lot as kind of right out of the gate. Cheap test. Every soil mechanics lab in the world can do it. Every first year soil engineer can do it. So cool tool. So we have 2 kinds of liquefaction, static and dynamic. Dynamic is the one mostly we worry about, especially in civil engineering structures, and that's typically earthquake loading. And there's the history of catastrophic failures because of this in the civil engineering world is legion. We can also get it by mobile equipment and blasting. Mobile equipment, we see that happen when you're trying to run equipment on with weak material. Your bulldozer sinks into the heap while it's trying to get it ready for the next lift. That could be bearing capacity, but could be static liquefaction or dynamic liquefaction caused by the vibration more than the weight of the bulldozer. Static liquefaction is a primary design constraint for upstream raised tailings dam. It will always be part of the operating criteria, and it will be expressed typically in meters per year. How fast can you raise your dam? How many meters per year can that crest go up? Because when you put that next lift on, it applies a load to the tailings, and and so it creates pore pressure in the tailings, and then that pore pressure dissipates over some time, and you want it to go all the way back down to 0 excess pore pressure, so back to hydrostatic conditions before you do the next lift. That constraint for tailings dam will typically be around 5 meters a year. It may be a bit more, be a bit less. And one of the very famous failures of the 2 catastrophic Brazilian dams, the Fundão Dam at São Marco, it had operated for a number of years with an average annual rate of rise of about 3.5, between 3 and 4 meters. Then the other bigger facility reached capacity. They had to divert all the flow to that impoundment. The last 2 years of its life, the rate of rise increased to 14.5 meters. And that's one of the trigger events that resulted in 19 dead. Upstream tailings dams, I can't think of one where 14.5 meters a year would be a safe consideration. Now, we're never going to have a catastrophic failure in a heap like that. The soil mechanics are identical. Our rate of rise constraints, if we have a liquefaction problem, would probably be a little more lenient. because the material won't be as bad as tailings. It won't be as saturated or as fully liquefied as tailings can be. So you might be dealing with something more like 10 or 15 or 20, but there'll be a number there for static liquefaction that you'll have to pay attention to. It won't generally apply to the heap, because if it's permeable enough to leach, it's probably too permeable for this. But in the Barrios dump where you're getting rid of it is another question. And I'll talk a little bit about that in a minute. So a common conversation or misconception is that heaps aren't vulnerable to this. Part of it is because if you can leach them, they're permeable. There's at least 5 projects where this was either predicted and then mitigated, or not predicted and then actually caused problems. 2 of them are Barrios dumps in Chile. The impact of those 2 is hundreds of millions of dollars in capital retrofitting, substantial impact on copper production over several years. The impact on this one has been many, many millions in mitigation and many tens of thousands of tons annual copper production deferred. So not trivial, but they also create fatal hazards. And on one of these, they had a couple of near misses where the big stacking system, which was supposed to work out on the Barrios, just about tipped over. And when those things go over, anybody near them goes with it. So it does happen. This is an earthquake liquefaction in Peru, and I have the name here because this was part of a published research document after the Moquegua earthquake of 1990. I'm supposed to know this stuff. I'm starting to lose it. Pandemic. Now, this is a copper oxide because oxides consume a lot of acid. They use interlift liners. So the liquefaction, which is pretty much a full liquefaction, full flow side liquefaction, but it was only the top lift because underneath that interlift liner, it was unsaturated. So this was kind of an inconsequential failure, a little bit of operational disruption. It could have been a worker hazard if there was somebody in exactly the right spot. So I don't want to trivialize that. Sorry, but nobody was hurt. The amount of damage that was done was really minor, probably under $1 million. A bit of disruption to operations, but not really a big deal. If this did not have interlift liners, these things can reach down 30 or 40 meters. So it would have been a vastly bigger problem, and this would have been a different kind of talk. This is one of the Barrios projects in Chile I mentioned. So you can't see it on the horizon, but the stacker is 1.5 kilometers away. And it just works back and forth. It doesn't get any closer. I'm standing on this Barrios. This is a few meters thick, and that's its stable depth. As soon as it goes more than about 3 meters, it flows again. And they're now building containment systems that are effectively a tailings dam. So you kind of have the worst of both worlds. You're handling it like a sloppy solid off the heap, and then you're building a tailings dam to hold it. No. They also had to reduce the height of their heap from 4 to 6, or from 8 to 6, and ultimately 4 meters. So it's the same mechanics on the heap. Leach cycles are a lot longer. Can't make their copper calls off of that heap. But on this side of it, that's what liquefied heap material looks like. So. Okay, so back to how do you screen this? How do you decide if you have a problem? Permeability devices are your friend here. Your permeability is high enough, can't liquefy. If the water can get out of the way of that contracting soil as fast as it contracts, you can't build excess pore pressures. And then it doesn't matter how badly you manage the facility, you can't liquefy. You can do other things wrong, but it's not going to liquefy. So lab permeability tests are really, I was going to say cheap, that's not quite true, but they're abundantly available, not unreasonably priced. Lots of mines build these apparatuses on site, so you can get lots of cheap data and quick. In situ testing is vastly better, but substantially harder to pull off. So we don't do that very often. The gold standard for liquefaction modeling is a family of different cyclic tests where you simulate an earthquake on your sample, and then you measure its response. How many cycles does it take to fail is really the test. So you have to have a design earthquake in mind, because it responds to amplitude of shaking and duration of shaking. So you may have to run this for multiple earthquakes, but there's ways to scale it to different, you can run it on one simulated earthquake and scale it up and down. So this will give you this will give you what's called the cyclic shear strength, which you then use to calculate the cyclic shear ratio, which is the shear strength versus the depth. In heap leaching, the problem here is if your material looks like that, how are you going to get an undisturbed sample to the laboratory? You could freeze it. Short of that, there's no way to do it. And there's not many sites where you can practically freeze material. We've actually done sample freezing in the Yukon for other reasons. It's a really big deal. So you're just not going to do it. And if you sample this material and then reconstruct it in the laboratory, you're not reproducing the fabric in the field. It's not really the same sample. This is a chemically created artificial soil that hasn't had any time to reach physical equilibrium. It's not like natural soil. And so, in fact, it's chemically still active because the pH of this stuff's pretty low. So trying to recreate this in the laboratory, for tailings, it's pretty good because tailings really is just kind of fine sand. But for leached ore, especially if it's an in situ heap you're trying to evaluate, I generally recommend against trying to get into cyclic testing, even though it's fantastic data. But if you don't have great samples, why spend all, and these are expensive tests, and you're going to ship this somewhere. You're going to ship it to, UC Berkeley in California or U of Texas, Austin, or someplace like that. You're not going to do this even in Chile, where they have fantastic facilities. Maybe a little, although we've had terrible luck with them. In situ testing, and there was a paper earlier today on this and another paper later, sometime I forgot when. Cone penetrometer test is a semi-quantitative test. It's semi-quantitative because it doesn't measure cyclic shear strength, but it measures things you can correlate with a pretty high degree of reliability. And from that, you get logs that look like this. But you can also calculate two critical factors. You can calculate the state ratio, the state factor. So if you go back to that critical state line, and if you're on one side of that, you're dilative and you can't liquefy. And if you're on the other side of it, you're contractive and you can. It calculates that line for you. So you get a graph, and it's called the state factor. And if your curves are on one side, you're okay. And if it's on another, you're not. And as a case in point, a few weeks before the Fundão Dam failed, they had a CPT rig on it. And because I was part of the review team, I got to look at all that data. Half of the profile depth of every hole was on the wrong side of that line. That predictive tool really works. The other thing it can give you, if you program in the earthquake, it will calculate the factor of safety based on its estimates of cyclic shear strength and cyclic shear load. And I recommend getting both of those graphs and using, because both of them are imperfect, both of them are semi-quantitative. So you want both of those and look at those, and those will give you a fantastic idea of your risk factor. And you can do lots and lots of these for the price of doing a few expensive laboratory tests. They can also give you things like pore pressure. And if you do pore pressure dissipation, you can get in situ permeability out of these, and some pretty good permeability numbers. That's the basic math behind how these work. The cyclic stress ratio is the stress induced by the earthquake, and then you divide it by the depth, so you get a ratio you profile with depth. And the cyclic resistance, that's the shear strength that you would get from the lab test or a CPT. You can do it with SPTs, but they don't work very well on our kind of material. Like if we got a nice clean sand, that's a good way to go. But for our material, the CPT is a better test. And there's also a misconception you can't do CPTs in ROM. I'll do CPTs on ROM with no problem. A lot of the data you'll throw away because when it hits a big rock, the data is meaningless. But until it hits a big rock, it's very useful data. So some kind of other indicators on whether you're going to have. Now, when we talk about flow slides in geotechnical engineering, we're talking about high mobility, nearly full liquefaction. These are the things that you see in tailings dams. We don't have a reservoir behind us to release. These are the things that are going to move hundreds of meters or even further. What this means is that you don't typically get penetrations of the failure zone below about 30 meters. because the confining stress starts to be enough to hold it up. So I generally limit my investigations to about 40 meters deep because it's not, liquefaction zone's not going to reach down deeper than that. Now you also have to pay attention though, when you're on the slope of the heap, it's that 30 to 40 meters below the slope. So your heap can be 200 meters high and the bottom 30 meters of that slope can fail, can liquefy. So you have to, there's some implementation issues on that recommendation. Some of the other effects are kind of the same with other stability issues. This actually, if you've got liquid limit data, that's a better number than this, but that's kind of an out of the gate. I mean, if you're running, your heap's running 15, 18%, you've got both a permeability and a liquefaction problem. Now I love this last one because we heard yesterday a couple of times about your permeability, yours should be 100 times your irrigation rate. And then, maybe you can live with 10 times. Well, your liquefaction risks kind of are down in this lower end. But the problem is that all 5 of those projects I mentioned before, they don't meet that criteria. They're less than 3 times the irrigation rate. So that ore exists, that stuff's out there. It doesn't mean you can't irrigate it, you can't leach it, you can't make money on it, but it requires a whole bunch of special things, and paying attention to this is one. And I already mentioned that 100% saturation is not required, in part because as it compacts, it gets more saturated, but also in part because it's variable. If your lab sample and basic data says it's only 80% saturated, that doesn't mean it's not 100% anywhere. And all it takes is one layer or one zone to have a problem. So 85 is a common rule of thumb. People use different numbers. So what do you do if you have it? Blending is your friend. If you've got enough good quality ore and you can blend it, that's the way to fix it, because then it also helps all of your other operating parameters on your heap. And there's some success stories out there. One of the projects I mentioned before that we're working on mitigating, that's the primary mitigation. Blending and monitoring water levels, saturation levels, and so forth. You thought I was joking when I told you I'd press the wrong button, huh? Thought I was messing with you. Rate of rise for your Repio stump. If you've got this kind of material, you have to raise really slow. Now, this is actually one of those Repios failures. This is, a kilometer or 2 kilometer, a kilometer and a half away from the discharge point. The rate of rise on this would have to be, to make this not liquefy, would have to be meters per decade. So that's just not going to work for this. That's pretty unusual material. So typically you can manage it with a rate of rise of your dump that's, 5, 10, 15 meters, something you can live with. Your footprint gets bigger because you can't go up to that 100-meter high as fast as you thought. You might not be able to go up to 100 meters. Improved drainage is always the answer to kind of every bad thing in geotechnical engineering. And wick drains are a fantastic tool. Freeport uses these routinely as a matter of policy. There's 2 heap leach projects in Chile operating with regular wick drain augmentation of their drainage. They're not free, but they're not horribly expensive, and the cost is absolutely predictable, and the benefit is absolutely predictable. So if it works, it's the thing you want to use. I mentioned interlift liners. I won't go back into it. Some preferential stacking. Keep your worst material away from areas where liquefaction failure is going to hurt people. I mean, ultimately. And if you can't do that, then make sure those zones don't have anybody there anytime you're irrigating that area. And I don't mean access restriction, absolute prohibition on people being above or below the slope if it's in a liquefiable state, which means it's either under leach or it's recently been under leach. Agglomeration for gold would fix this because the cement gives you cohesion, and cohesion isn't part of that equation I gave you earlier. So the full shear strength equation is confining pressure, effective confining pressure, so minus pore pressure, times tangent of the friction angle, plus cohesion with no correction for pore pressure. So the cohesion you get from the cement survives the pore pressure. So, but gold ores it's pretty rare to see a gold ore that's anywhere near this though. So this is an sulfuric acid leach problem. This is a poor quality copper ore or a nickel ore, maybe a uranium ore. I don't want to say that gold ores won't liquefy ever. I've seen some pretty bad stuff out there, but it's a pretty rare project where that would be something to think about. So, questions? Should I push this other button now? Did I run overtime? Yeah. You're being very polite. No? Please.
Thanks. You mentioned that if permeability is high enough, then excess pore pressure won't develop. Do you have a rule of thumb for how high?
Yeah, that's a good question. So in my little table there where I said when you're vulnerable, I said 3 times the permeability is at least 3 times the irrigation rate. That doesn't mean it can't liquefy. It just means it became much less likely. If I mentioned before that there was talk yesterday about 100 times being the goal, 10 times maybe. If you're at 10 times the permeability, then I would say you're done with screening. It's not going to liquefy. If you're less than 10, but above 3, now you kind of have to do that hard work. If you're below 3, it's vulnerable to liquefaction. So, okay. So, thank you.
So I encourage next year for people to raise their hand to be a speaker. You're getting this nice Thule bag.
Thank you very much.
Thanks. Okay. So our next speaker is Caleb Cook. Caleb is a project engineer for Caps Cassidy Associates. He will be presenting pulp agglomeration process and application for gold and silver operations.
All right. Can everybody hear me okay? All right. As our director said, I'm Caleb. I am an engineer at Capas Cassidy Associates here in Reno. Today, we're going to be talking about pulp agglomeration, what it is, when you might consider using it, some of the design implications for it, as well as a quick snapshot at some of the mines that have successfully utilized pulp agglomeration. So, what is pulp agglomeration? Pulp agglomeration is a hybrid heap leach and cyanide milling process in which a milled slurry is combined with coarse crushed ore along with cement in order to form stable agglomerates. These agglomerates are then stacked onto a leach pad for further leaching and metal recovery. This technique, as described here, was first utilized at the Castle Mountain mine in the early 90s. The flow sheet used at Castle is similar to what is presented on here. So the ore was crushed. The low and high grade ore was crushed in a shared conventional crushing circuit. At Castle, they used a gyratory crusher. Here it showed as a jaw crusher. The high grade ore was then milled in a single stage. The milled material was then thickened, followed by filtering. The filtrate and the thickener overflow contains leached metal values, which were then sent directly to the ADR recovery plant. The filtered cake was combined with low-grade ore and agglomerated using an agglomeration drum. That was then stacked onto a leach pad and leached for further recovery. So, why consider pulp agglomeration? For Castle Mountain, this came down to timing. They found that they were not getting the recoveries that they wanted with their high-grade ores, and the time to permit a tailings impoundment was going to be prohibitive to the project. So pulp agglomeration ended up being a nice compromise for them. In the case of Dolores, which is another mine we're going to talk about, they began operating as a standalone heap leach, and their project site was restrictive on space. They did not have any room to build a tailings pond. And so they found that by utilizing their heap leach along with pulp agglomeration, they are able to get higher recoveries as well as store the mill residue on their leach pad. So other considerations, there can be some capital savings with pulp agglomeration as you do not need to build a tailings facility. The mill residue is stored in the heap. And there is also environmental and cost savings. Cyanide destruction is not required. And yeah. So with all of the heap leach and mill projects out there, how come we don't see more pulp agglomeration projects? One of the big reasons is that there is a lack of familiarity with the technology. People don't know about it. They don't understand the mechanics behind it. And so they do not use it. Other reasons why, with pulp agglomeration, it does require a steady amount of both low grade and high grade ore in order to be able to operate the process. You also will be deferring some of your metal recovery to the leach pad, where if the leach pad is not run properly, there is increased risk that you might not realize that metal recovery. And ultimately, the most significant added risk with pulp agglomeration is that you are introducing additional fines to the leach pad, which may result in increased permeability concerns. So if you look at this, a good, well-behaving leach pad, you apply solution to the top, it permeates and percolates down to the drainage later, you collect it, and it goes to your recovery plant where you recover the metals. If you develop zones of poor permeability, you can get perched water tables, underleached or unleached regions of your material, which can ultimately result in stability risks as well as loss in production. So this picture right here, this is from a failed compacted permeability test, and you do not want to see that inside your leach pad. So how can we prevent this? The answer is test work. A lot of people don't like to hear about it. It's slow and it's not always the most fun, but it is very important in order to determine your project to make sure it's successful. And the very first thing that should be done is looking into the economics. I'm a firm believer that if the process does not make money, you should not use it. So in order to determine what your potential economic benefits are, you need to first look at what your recovery improvements are with your material, what you gain by grinding, as well as what your target crush sizes need to be for the low grade ore and what your mill proc size. The next is looking at the permeability. That would be the ratio of the low grade ore to the high grade ore, the cement required to maintain a stable heap, as well as ultimately what your planned heap height is. And then last, you need to look at your global process. Can the mine provide the tonnages required of low grade, high grade ore, and what will that look like? So getting into a little bit more of the details on some of this, the most important thing once you've kind of established a baseline of what your crush size and grind sizes are going to be, as well as what you are going to want to do. The next thing is determining what your compacted permeability is to ensure that you have a stable functioning heap. So the considerations for that include what your heap height is going to be, what your blend of low grade ore to high grade ore is, how much cement you need to apply in order to achieve stable agglomerates. In a typical program, we will look at multiple different cement addition ratios, and the goal is to determine what the least amount you need to maintain adequate stability and safety factors. So this is a typical compacted permeability test apparatus that we utilize at our lab at KCA. Right here, this is the test cell. It sits on top of a load cell right here. There is a hydraulic ram, which applies a load to the ore and simulates a approximate heap height. Not pictured on here is a solution reservoir that sits on top of the tank. Solution is added to the ore from the tank, and then the flow is measured coming out the bottom. With these tests, we look at the flow rate coming out. The material slump, that's the difference in height from when we started the test to when we concluded it, as well as the solution clarity and color. If you have cloudy or muddy solution coming out, that's an indication of fines migration. as well as a failure of some of the agglomerates. Material slump, we're usually looking for less than 10% for a passing test. And then solution flow rate will vary depending on how large your test cell is. But in this cell, usually 10 to 14 times what your design application rate is, would be considered a passing test. Pictured here, these are samples before and after compacted permeability testing. So here you can see nice round agglomerates, very little fines present. So these are well agglomerated. This test is afterwards. You can see that there's some breakdown of the agglomerates, but overall this is pretty good looking material, and it ultimately ended up passing. Other test work, as I mentioned, you want to determine what your recovery requirements are going to be and what you need to do to achieve those. So that includes column and bottle roll tests, generally at multiple different crush sizes and grind sizes. And then later in some of the final stages, it's also good to revisit the column test work with a blend of your agglomerated material with the low and high grade ore, just to confirm the results. Physical characterization test work, such as abrasion indices, bond and ball mill work indices, those tests in order to be able to appropriately size the equipment, as well as the solid liquid separation, the rheology, the filterability, the thickening, so you can manage the water and ensure you have the correct moistures going to the agglomeration drum and to your heap. So next, we're going to take just a quick snapshot at some of the projects. Castle Mountain, it operated originally from 1992 to 2004. It's located in San Bernardino County, California. The flow sheet considered a shared conventional crushing circuit. It crushed the ore in 3 stages to 80% passing 3/8 inch. The high grade ore was then ground in a single stage ball mill to 80% passing 100 mesh. The high grade ore was then thickened and filtered using disc filters. The filtrate and thickener overflow were recombined, and that material was sent to their ADR recovery plant shared with the heap. And then the filter cake was then repulped and then pumped over to the agglomeration drum, where it was mixed in the drum at a 3.5 to 1 ratio with the low grade ore and 8 pounds per ton, or about 3.6 kilograms per ton of ore. And the overall ratio of the ore to the heap was 6.7 to 1, low grade to high grade. Not all of not all of the low grade ore goes through the drum in order to just maintain smaller equipment sizing and cement additions. The next project is the Ruby Hill mine in Nevada. Ruby Hill is a long operating mine. However, pulp agglomeration was introduced in 1997. At Ruby Hill, low grade ore was processed at the rate at which it was available, which was generally in the 1,600 to 3,150 short ton per day range. The ore was crushed in a 2-stage crushing circuit shared with the high grade ore mill. The high grade ore was then crushed with an additional 3rd cone crusher, followed by single stage milling. That material was then thickened and filtered using belt filters. Again, the filtrate and thickener overflow went to the recovery plant, and the filter cake was combined with low grade ore in an agglomeration drum and stacked onto the leach. Last project we're going to talk about was the Dolores project. Dolores was a 16,000 ton per day heap leach that started operation in 2009. Pulp agglomeration was built in 2017. This is the entire pulp agglomeration circuit you can see in this picture, which KCA designed and built. The pulp agglomeration circuit includes a dedicated 2-stage crushing circuit. This is the primary jaw and secondary cone right here. The crushed product stockpiled here in this radial stockpile, reclaimed and fed to a two-stage milling circuit consisting of a primary rod mill followed by a vertimill for grinding. The milled product went to a filter feed tank, which also acted as a single-stage leach tank. The slurry was pumped to 3 pressure filters operated in parallel. The resulting filter cake was combined with low-grade ore in a mixer before being fed to the agglomeration drum, where it's then recombined with low-grade ore from the existing heap leach crushing circuit and conveyed onto their leach pad. The filtrate from the filters was clarified using a pin bed clarifier to remove any suspended solids and then pumped to their existing Merrill-Crowe facility. So for Dolores, the low-grade ore was processed at about 16,000 metric tons per day. The mill product was ground at 5,440 tons per day to 80%, passing 425 micron. That's a typo. The low grade and high grade ore were blended at a 1-to-1 ratio in the agglomeration drum, with the overall low grade to high grade ratio being 2.9-to-1 going to the heap. And for cement addition, they measured it based off of the high grade ore only, which was 20 to 30 kilograms per ton, which that works out to be about 6 kilograms per overall ton to the heap. And just a few pictures. This shows the active stacking phase during commissioning. Here you can see some of the nice agglomerates from the agglomeration circuit, along with some of the blended low-grade ore that was not agglomerated through the agglomeration drum. You can see the agglomeration drum right here, as well as they were metering high-strength cyanide to the agglomeration drum to help jumpstart the leaching process. And in conclusion, pulp agglomeration is a proven and viable processing option where applicable. Pulp agglomeration provides costs and operational advantages compared to conventional heap leach and milling options separately. It may not be suitable for all heap and mill projects. However, it is most likely underrepresented in our industry. Heat permeability is the main risk for a pulp agglomeration project, and test work is critical to determine the operating parameters and viability of pulp agglomeration. Thank you. Oh, I think they're bringing you a microphone.
Yeah, great presentation. I've got 2 questions for you. So did you have any mixing equipment ahead of the agglomeration drum to mix the filtered product with the ore?
So at Castle and Ruby Hill, they did not have any additional mixing equipment. However, at Dolores, we did install what the actual name of the equipment is, a mixer, which is kind of, it looks like a mineral sizer almost, but a little bit different on the insides, where they just blended the cake. And the primary reason for that was to break up the filter cake a little bit more before it gets to the drum. That way you don't have big clumps of filter cake that doesn't get properly agglomerated. Dolores also initially tried using something called a delumper, which they utilize in a lot of paper mills. It just spins really, really fast to try to shred the material. And it ended up being the most expensive chute they ever put in.
So the related follow-up question is there any reason why you couldn't put a pulp, so a thickener underflow to blend with the rock, assuming you can not exceed the water requirement for the agglomeration step?
No, there's absolutely no reason, so long as the blending ratio and everything shows that you're getting a stable heap. Some projects have looked at not using filter presses. At Dolores, they didn't use a thickener. They just went straight from the thickener feed tank to the presses. And if you're blending at a high enough low grade to high grade ratio, it's possible that you don't need anything. You just mix the slurry directly into the low grade ore. But again, that's probably getting a little bit riskier. And yeah, so there's no reason why you couldn't get by with only a thickener or only a filter press, or it's possible you might not need either.
Is your, at Dolores, is the cement addition and ratio, are those relatively constant? And if not, is it, you know, do you have a control, like operating curve to decide how much cement to add, or how do you control that?
I was actually recently talking with Americo Delgado, who is one of the operations advisors at Pan American Silver. He kind of oversees multiple of their mines, and the cement addition is fairly constant. Although they base it entirely off of the high grade ore going to the heap, so they're measuring the weight of the filter cake using belt scales, and that feeds back to the silo feeder to administer the cement addition. They're actually adding a little bit less than what they're originally planning on. So right now they're closer to that 20 kilogram per ton of high grade ore number. Hopefully that answers that question.
Have I got time for one more quick question?
If not, you can find me after. I'm happy to talk.
Running a little bit behind schedule, sorry. Okay, so the next presentation is by Mr. Mike Yao. Mike is the lab director for geosystems analysis, and he will be presenting a laboratory and numerical approach to assess ore consolidation and solution distribution during ramp-up period.
Thank you, Francisco. Good afternoon, everybody. So first, I would like to thank all my geosystem colleagues for their support of the work and experimental modeling, and also back and forth idea sharing and discussion from all my colleagues at Geosystem, of course, the sponsor from the mining company. And today, I'm glad Mark already went through the worst case liquidation, and also Caleb always say, yeah, test works. So I'm going to show you some laboratory work, and then to deal with the consolidation issue during the ramp up period. So the problem is that in the ideal world, so we apply solution, and solution was assume uniform going down there without stock and arrive on time. That's perfect case. However, in the real world, we know the solution is normally not uniform, and then the performance efficiency always tied down to the solution distribution in the heat. And so the real problem is we normally, so I think the worst case right now is we don't even deal with the deep. We at the start, if you don't start out carefully, you weather the profile, the agglomerate or non-agglomerate ore at the target irrigation rate. Suddenly you load a very wet condition to a not well prepared ore, and then suddenly the sudden wet actually have a tendency to collapse the ore structure. It's not liquidation, but ore structure do collapse. And what happens? They consolidate, and then due to the consolidation, the solution actually went around, avoid those consolidated area and go around, form the preventive flow. And those behavior actually, they just keep transmitting downward. So if you don't do well, then you have a problem at a hello. So don't, and this is a reversible process. In hydraulic point of view, you cannot really recover from the situation. You have a different consolidation, and the pressure flow is everywhere. So you forget about your efficiency for leaching. So, and then the experienced operator normally deal with this by the ramp up schedule. So they slowly kick in, like a plane take off. So they make the water wetting more smooth. However, this is based on the personal experience, and what the base and how the works is not really well understood. Now, this is an experiment we conducted a few years back at Geosystem. And then this topic will be presented by Mike Mazzarica in tomorrow's section. How it's a little bit by accident, we reverse that. So I wish you can see this, so I don't have to cover this again. But so what happens is that you loaded the full scheme of irrigation at the start. You can see at the starting about only 2 hours, the center of the ore sink down about 10%. And then within 24 hours, this is agglomerated ore. They sunk down about the 16-17% in the center. And then the edge actually sunk down to 12% of the total column height. So this is serious consolidation. If you are not careful, you apply the solution as forced irrigation at the start, you will get this type of result if a ore is not that competent, and then the agglomeration or non-agglomerated ore, they are not so strong to sustain this type of wetting process. So at the bottom, and this is after a certain time of this irrigation, and then we apply the dye into the column. We also found that this when with a greater depth, you can see what actually escaped to the central area where the consolidated area were avoided and what actually went around. They prove there's a residual flow occurred due to this. And again, you are now wetting this ore properly. So the objective for us is we try to develop a method we can determine the wetting and the consolidating behavior for agglomerated and non-agglomerated ores. So the optimal cycle, and we want to determine that, but we need to develop an approach how to get that done. So we want to, the purpose, we want to reduce the potential of agglomerate structure collapse and achieve more uniform hydraulic property, or in terms like more uniform solution distribution in a profile. And we want to apply solution in an intermediate way. It's like on and off. What happens is that if you put a small slug of solution down, which will impose a very small impact to the ore, and that they will not wet too much, then use the bared capillarity force in the ore itself, and then they pull down more evenly. So with alternating on and off, it actually has better chance to get more uniform solution distribution. And in this study, we also want to demonstrate how the solution distribution can develop during the off period. So eventually, we want to see if we can develop some kind of scenario to help optimize the ramp-up scheme. So the approach we take, we will combine the laboratory test and the numerical simulation to investigate the collapse in the irrigation ramp-up. How do we do that? So we start with a hydraulic property test, like Jason went through some flexible tests. We measure the saturated conductivity, unsaturated conductivity, and moisture returning curve. And we use that to develop a set of hydraulic property function, such as magnetic parameters. We plug those numbers into the numerical model. We can simulate the solution distribution. I'll go over that a little bit later. And we also develop a crucial test. We call the ore consolidation test, or call the wet pack collapse test. So basically what we did, we just use a agglomerated ore, and then we introduce the pressure, and then by gradually step up the solution content, and then see when the major collapse will occur. Because there's no stranger for collapse under the wet condition in the soil science. Because like a lowest material in the China area, they when they face the water weather surface, the major collapse start occurring. There's many years and many research done in this area, but still no easy or conclusive model can be concluded for this type of behavior. So it's a very complex process, but we intend to use a so-called critical solution content, which means at a certain water, when we meet a certain water content, and then the ore major collapse will start, we will try to avoid that to happen. So with that in mind, we use the typical unsaturated flow modeling, so we can simulate, and by putting the parameter we develop in the laboratory test, we plug into the flow modeling, we can study the vertical water content solution content distribution, and about lateral and vertical, so we can generate 3D domain solution content distribution for this. And from that, so we will try not to hit the critical solution content. So the major collapse should not be experienced in heap leaching condition. And for the case study, we use 4 different ore type, which have a very similar porosity. Particle size distribution with very small variation in that. Even with very small variation, however, they still experience a quite a bit different property difference. And this is a parameter after we did all the laboratory test work, found all the saturate, K-sat, saturate, K-on-sat, and then moisture returning curve. We developed parameters, but then we plug it into our model. And I would elaborate a little bit about wet pack collapse test. What we did, so we prepared the agglomerated ore, let it rest, and then with a target time, and then we packed the leach ore into the dual wall permeameter, like shown in the bottom. Then we compressed from the original agglomerated water content, and then we slowly compress from the 0.5 to 5-6 centimeter for targeted shallow depths, and then by steps. And to finish that, we record how much bulk density change increase due to the compression. And then we increase the water content by 1-2%, and then we pack again through the same process. For that, we repeat about 5 to 6 cycles until we find a major collapse. And at a target water content, we define that water content as a critical solution content. As you can see here, this is ore type 3 and 4 and 1 and 2. So for ore type 2 and 4, you can see the critical water content was found right around the major collapse of structure at about 22%. And for ore 1 and 3, they were like about 19. I'm sorry, the first one is at about 19. This is about 20%. For ore in the 1 and 3, they are about 22%. So when the major collapse start occurring, so we will try to do everything we could to avoid the in any profile to reach that. And I come to the modeling. So we have developed the established the criteria for the solution content, the critical solution content. So we'll not try to hit that. So then we come down to the simulation. In here, we put the emitter here, and then we apply the solution through the emitter. And in a 3D domain, use a Hydro 3D. And then this is about 6 meter depth and a 25 centimeter in diameter to represent the usual spacing between the dripper. And we run the model and apply the different scheme. This is a little bit complex, but I will get a summary. But in general, we start out with a no ramp up for the standard no ramp up irrigation into the model. And also we apply the very slow scheme. Start with the 168, the full rate about 6 liters per meter square per hour, and it's probably equivalent to 0.0224 GPM per foot square. And so this is a very slow scheme, and the total would take about 15 days to complete. And also we introduce a slightly faster scheme, the same flow rate, but with about 0.5 hours on time. And this one, for example, I forgot to mention, 48, we probably have 0.5 on, and then almost 1 day, 23.5 hours off. So they achieved the 1/48 of the full irrigation rate. That's a part of the starting ramp up. So this one, 132, is slightly faster. And then the scheme 2, and it's about 132, but with additional slower on time, so which has a little bit less load, but more frequent irrigation period. And scheme 3, and even faster. This one take about four days to complete with the same flow rate. And so we also varied about between the 0.25 and the 0.5 hours. The purpose of that is because, like I mentioned, the on-off actually help the spreading of solution. And then we want to keep the loading as small as possible to even out solution distribution. And scheme 4, the purpose of this is try to repeat the scheme, slow scheme, but because they have a very slow start as a slow scheme, but later we accelerate. So we try to save a little bit ramp up time. So hopefully it can be shorter without affect the consolidate, the collapse structure. So this is a summary. So just like we can see the slow scheme, and then scheme 4 has a slow is a start, and then the scheme 4 has about say 3 days compared to 15 days, while scheme 1 to 3 they all accelerate to a certain degree. So this is a typical water content profile we simulated from this model. We can see this is a cumulative irrigation from the surface, and then with a incremental that the ingression, and then each profile, a curve showing the depths right under the dripper. So it's probably the wettest spot right under there. So you can see the very shallow depth, 5-10 centimeter, all the water went over the critical solution content. That means they collapse the shallow structure. However, starting from around 50 centimeter, after like a 25 centimeter, 50 centimeter, which is the purple line here, they stay well under the critical solution content. That means the shallow structure can get collapsed, but about to 20-30 centimeter. But after that, the solution content does not meet the critical solution content. So they will try to hold the structure the best they can. And this is showing just a vertical profile. As shown on the left is a continuous scheme, which is like there. If you're doing the model does not handle collapse or consolidation. So they just consistently grid. But you see there's a constant pattern, but reality is not like that, because the reality, like I showed in the picture in the earlier test work, they keep collapsing and they generate potential flow. So, but this model cannot handle it, but they're just showing, this is the model showing the continuous. And while compared to on-off, which is the power of on-off, you can put a small slug of water solution and then let the rest of the time and the capillary do the action, and it will pull the water spread, and then very even wetting process can occur. So it shows the sample number 3, and this is again the vertical profile right under the dripper from 0 to 3 meter depth. And the horizontal is the solution content distribution with about 1 inch of water applied. You see the shallow collapse, and they all went over the critical solution content as the red line shows. And with a 4 inches solution, you can see here, and the collapse at shallow is still there. And all other scenario, they kind of went higher, but they're very close to the critical one. They did not exceed. But when you apply about 7 inches of solution, and then only the scheme 4 and then slow scheme survived. And after about 7 inches with all 4, the one we show was just the other, only one ore. This is ore 1 and 2. And then you can see only the red one is a scheme number, slow scheme. And the yellow one is scheme 4. And both schemes survived from the collapse. And then while the other scheme actually start experiencing the major collapse. And this is for all the case for all the 4 cases. And we also look at how uniform they are in a horizontal way. So this is on the left, this is ore 1 and at about 15 centimeter from the 0 to 25 centimeter. Remember, the emitter is from here, the lateral spreading for the solution distribution. And then this one's at 30 centimeter depth. So at the 15 centimeter depth, you can see really non-uniform expected, because and then they collapse in the central area near the dripper. And then on the right, and it's showing when they go down deeper, a much uniform solution distribution can be achieved. And then the ore 2 actually is a way more unstable than ore type 1. And then 3 and 4, they all show the similar. I think I want to demonstrate this. And we can see here with the 15 minutes irrigation, because it's more smooth, a short period, actually generate the most uniform solution distribution among all the scenarios. However, those 15 minutes of irrigation schedule is hard for mine to comply, because it's probably more sophisticated and it may cost more operation. They go up the operating cost. So it's probably may not be feasible for the mine to use this type of irrigation schedule. to conclude this talk, so we use a Webpack test, and then we can find the critical solution content. And for example, from the 19% to 22% for all the 4 ore. And then we also identify different irrigation scheme. We plug in the irrigation scheme into the model, see the generated distribution can protect all the ore from space and give a uniform solution distribution. So, and then what we found for a slow scheme and a scheme 4, and they can protect the ore from collapse at the shallow depths. And then and then they collapse at the shallow structure between 20 and 50 centimeter, but from that on, all the ore will not collapse. They only experience the shallow collapse, but from that on, they are very smooth. And then, and the scheme 1 to 3, actually, they have a very similar solution distribution pattern throughout all the simulation. So between scheme 4 and slow scheme 4 actually saves some time by accelerate the irrigation rate toward the end, but still provide a similar behavior like a slow scheme, so which we can accelerate the ramp up period. In the 15-minute scheme, it may not be operatable, but however, they probably provide more uniform. If none of the cases works, we can consider to decrease the irrigation time to protect the consolidation. Thank you very much.
Hi, Mike. Thanks for the chat. I guess I had a question for this particular, or the solution used for the testing, was it acid modified, or was it for a copper ore?
Raffinate.
It's raffinate?
Raffinate solution.
Okay.
This is for all 4 are for copper leaching.
Did you see any difference in the rate of copper recovery between the columns that did consolidate and settle?
We did not do a metallurgical study. Most of our studies are focused on a hydrological study. So we just study for solution distribution.
Okay.
How they change throughout the test.
Thank you.
Yeah. Thank you.
I promise I was going to pronounce this well. So next presentation is Chaitna Sinha. Chaitna is a consultant for KPS Associates, and she will be presenting mining practice and capacity building based on ESG principles.
Good afternoon. Thank you so much for the opportunity to present. Before I begin, I'd really like to just thank my co-authors, thank for their invaluable support and thoughts and the dialogue, which I think has just been really, really engaging. And we hope that you will appreciate that it will be useful for you as well. But I just thank you to Mr. Sinha and Mr. Smith. So just as a little bit of background, I work primarily, I am an attorney. My practice is primarily focused on indigenous communities and federal Indian law. So I come at this from a little bit of a different perspective because I have seen a lot of these types of issues, not from the technical side, but not from the technical perspective, but from the ESG side. So on one hand, life without mining in the current day is difficult to imagine, as any of you who might be tempted to look at your cell phone are understanding. On the other hand, mining has done and continues to do significant environmental damage around the world. Further complicating this dynamic is the fact that neither the benefits nor the impacts of mining are distributed equally. But the world is changing. Today, both regulators and individual community members are increasingly scrutinizing every aspect of mining. Tolerance for environmental damage is lower. Traditionally marginalized communities have increasing power and resources, and social media has made it easy to nationalize and globalize an issue. For any of you who might have followed the Dakota Access Pipeline issue or the drilling in the Arctic National Wildlife Refuge controversy, you've seen how this works in practicality. Communities are more vocally demanding that mining operations be conducted in a manner that is ethical and economically equitable, that mining not be done in culturally and environmentally sensitive areas, and that in areas where it is occurring, it be done utilizing best available technology to minimize environmental impacts. To see how this is playing out, all you have to do is look at some recent headlines. So in Brazil, they announced an investigation into the Valle Dam failure to determine whether Valle colluded with auditors to overstate the dam safety in violation of Brazil's 2013 anti-corruption law. This, if found guilty, Valle could be subject to a penalty equivalent to 20% of its 2018 gross proceeds. And this has also triggered a call for regulatory reform, with Brazil considering reform that would result in regulations that tighten dam safety. In Geneva, a Swiss court found magnet mining Steinmetz guilty of bribing Ghanaian officials for a permit to mine ore. Environmental and cultural risks are also a source of controversy around the mining industry. In Nevada, we're not too far from here, community members are concerned about the reopening of the Idaho-Maryland mine. They're concerned about the well water, the impacts that the operations may have on air quality, and they're asking questions about whether this is the best use of land resources. In Arizona, members of the San Carlos tribe and others are protesting a proposed copper mine that would be sited on land that they consider sacred. In Utah, communities surrounding a uranium processing facility are protesting because they are concerned about the potential impacts of this facility on the air, the water, and other resources. So the opposition to mining is not limited to environmental issues, nor is it limited to the United States. In Peru, indigenous communities are protesting mining operations in large part because they are concerned that they are not seeing adequate financial benefit from these projects, although their communities bear the burden. In Serbia, thousands flooded the streets to protest proposed legislation that would fast track mining, impacting private property rights, and potentially fast tracking projects that community members consider environmentally damaging. So the point of highlighting these examples is twofold. First, to demonstrate the nature and extent of the controversies surrounding mining, and second, to underlie the continuing need for development in ESG, which is where our paper focuses. So there's no doubt that the industry has come a long way. Words like ESG, capacity building, community-based monitoring, and social license to operate are now used not only throughout the mining industry, but they're used in the corporate world and the public sector. And they're being used for all kinds of purposes, from planning to development. So this is part of the solution to some of those headlines. As context, I know that many of you are familiar with this, but for those of you whom this may be new, ESG and the mining industry refers to the industry's approach to managing air, water, and soil pollution, treatment and attitude towards employees and the broader community, and management practices like diversity, transparency, good relationships with regulatory and non-governmental organizations. And this isn't just this is starting to be adopted not only in the industry, but in other areas as well. The Toronto Stock Exchange requires disclosure of financially material E&S factors. The US Securities and Exchange Commission is looking at rules regarding greenhouse gas emissions. The London Stock Exchange has issued guidance involving best practices for reporting ESG. All major accounting houses and major stock analysts include ESG in their review and rating processes, and major mining engineering companies now provide ESG services. According to a survey, so capacity building is an aspect of ESG. So capacity building points to improving communities' understanding of a project's long and short-term goals and implications in a concerted effort to eradicate the hurdles caused by lack of this understanding. So that's a lot of words. How's it working in practice? Well, generally ESG has been put into a couple of different categories. You see ESG efforts in the context of education, where you see industry investing in things like funding schools, scholarships, mentoring programs. You see ESG efforts have also focused on employment. So both within the mining industry, you see a lot of efforts to try to create jobs for local communities as part of ESG efforts within the mining industry. And you see some support for non-mining related local endeavors. You see lots of efforts in ESG in the context of community development. So infrastructure, planning, job training, workshops for local entrepreneurs, funding of micro enterprises. And you see efforts in community engagement, meeting with councils and the public, and collaboration on things like public health, welfare, and safety. So the current issue of Global Mining Outlook, an annual report put forward by the international consulting company KPMG, ranks environmental risks, including new regulations, as the #1 risk for the mining industry. Community relations and social license to operate ranked 3rd on the list. In view of the continued controversies and ongoing concerns, it's important to look at where we are, how we're doing, and what more needs to be done. And it's in that regard, that's where I'd like to focus the rest of my talk. So I want to start by saying that the efforts that have been made towards capacity building and ESG so far are important. They should be continued. They need to be recognized as the significant steps forward that they are. But there's something missing. There's limited, and all of the things that I've listed and that we've discussed in the terms of capacity building, there's limited or no efforts for building internal capacity, for understanding mining processes and its implications, community-based monitoring, funding for resources such as external advice and consultants, and it doesn't increase capacity to advocate or bargain for better environmental protections. And again, this isn't to dissuade the efforts that have already taken place. It's simply to say that there is a gap in where those efforts have occurred. All of the efforts that occur that we've identified focus on capacity building in the context of overall social benefit. But limited efforts have been focused on building capacity within affected communities to advocate for mining practices that will better protect communities. Few of the capacity building measures that we've identified will result in affected communities being able to bargain with the mining industry on a meaningful level about the nature of its operations, such as the types of waste generated, impoundment designs, monitoring programs, or reclamation plans. And these are areas that are ripe for continued community participation. And they're also the types of issues that frequently result in the most significant concerns and impacts to the community, and where disputes are most likely to occur. There are limited experts willing and able to provide technical support to affected communities, and often affected communities and environmental organizations lack the funds necessary to hire these external supports. So why is additional capacity building needed? I think that it's useful to look at this in two ways. First of all, the mining companies can't be successful independent of community, independent of the communities, and they're rarely in a position to fully understand the community's needs. They often are not local. They often are operated by people with differing community and cultural values. Mining operations often lack traditional knowledge and involvement. And industry itself, even when wishing to engage, may not know how to best achieve this. These are all areas that capacity building can help with. From the community's perspective, as we discussed, they often don't have the technical expertise to provide technical feedback, but they also may need additional support to answer questions like how do we protect the resources? So a really good example is communities will often say they want cultural resources protected, which is an important and critical statement. But if you go behind that, it's much harder to delineate what those resources are, how they will be impacted, and what measures can be taken to minimize risk. These are all questions that the community may not have the resources to answer. These communities also often are already dealing with a variety of socioeconomic issues. So capacity building is needed because without additional resources, they may not be able to fully engage with the mining industry. And the offset of this is if they don't have the additional resources and they can engage, the easier answer is just no, right? They're going to oppose these projects, and there's going to be limited opportunity to engage with them without additional and try to change that perspective without additional capacity building. Capacity building can help bridge gaps and mitigate some of these differences. So what specifically are we looking at? What do we think could help? Funding opportunities for information sharing and engagement with surrounding communities to mitigate cultural resources damages. As I mentioned, it's difficult. This is an issue that comes up frequently when talking with particularly Indigenous communities. And it may take things like identifying cultural resources itself can be a barrier, and there are data gaps there, and filling those data gaps can require anything from ethnographies to biological surveys, which take time and resources, right? So when you ask a question like, how do we protect cultural resources, to fully answer that, there may need to be an additional data collected, which requires time and resources. And that's an area where capacity building could help. Increasing the technical capacity of communities, NGOs, and regulatory agencies. So oftentimes they lack the technical expertise to offer technical solutions. They have strong values and they understand their local environments, but what they pretty frequently lack is technical support and technical expertise to offer comments specifically on how operations could be changed to better align with community values. And finally, there's an opportunity to engage communities in accountability measures, such as monitoring. In many cases, there is infrastructure within existing communities that could be utilized. Several tribes have robust environmental divisions and well-trained staff, and these entities could house and offer support to a community-based monitoring effort. There are oftentimes NGOs that may be well situated to house these types of efforts with a partner on these types of efforts. So there are resources within these existing communities that could be further expanded and further utilized. So looking to the future, I think it's really important to look at a couple of concepts that you're increasingly seeing both in general in lands management, and that I think you're seeing in regards to Indigenous rights. So free, prior, informed consent is a specific right that pertains to Indigenous peoples and is recognized in the United Nations Declarations of the Rights of Indigenous People. It allows them to give or withhold consent for a project that may affect them or their territories. We're seeing this being an increasingly important concept in Indigenous communities. The social license to operate is now taking on a different context. It's not enough to share the benefits of mining. Communities want to have a say in how mining is done, and they want to have a say in what happens after the mining is over. Indigenous rights are continuing to gain strength. Indigenous voices are continuing to be very important politically, both domestically and globally. Social media and public awareness, it is not possible to keep an issue localized anymore. If there is enough opposition, it will become a more national, state, global issue. And co-management and collaboration. I think we touched on this a little bit earlier, but communities want to partner with mining operations now. If it's going to occur in their communities, they may not always, there may be cases where they simply oppose it, but if it is going to occur in their communities, they want to have a voice in how it's done. They want to understand the long and short-term repercussions, and they want to be part of that process. It is happening in the public land process. You're now seeing tribes having an increasingly important role in how, and not just collaborating with how lands are managed, but actually not just providing input, but actually collaborating in how lands are managed. And I think that concept of co-management and collaboration is going to find its way into all aspects of land use, including mining. So this is the future. Capacity building is an opportunity to help the industry approach the continuing social issues. There are tools in the toolkit that the industry can use. We've named some of them, but somebody said earlier you need an intermediary layer. I think capacity building is an opportunity for the mining industry to help build that intermediary layer. Thank you. So, sorry, one other important slide we should cover, of course, industry needs to get benefits of this. So the benefits from doing this are less public opposition, permitting, fast track for permitting, better feedback on how to meet community needs, and less likelihood of protest, obstructions, and litigation. Thank you. Questions?
Great talk, lots of things to think about. Just as a general observation, having worked with tribes and known people that have worked with tribes over the last 30 years in the US, these communities go back centuries. And when you want to talk about small town politics, it's really small town politics times orders of magnitude in terms of rivalries, competition within the community. And so it often, the serious politics that goes on in communities can negatively affect a project, even though it may have nothing related to do to the project. So what are your thoughts about how industry can approach those issues?
So I think it's important to look at the structure of the entity that you're talking about. So you referenced tribes in the United States, and yeah. So I mean, the reason I'm bringing that up is because tribes in the United States have a specific governmental structure, right? Whereas and globally, or if you're dealing with tribes in other or indigenous communities in other places, their structure may be different. But for tribes in the United States, where they have uh, a set government structure, I think that the correct approach is to start with defined government leadership and engage the government leadership to ask them if they want you to engage the community. Because I think that ultimately it is, it is the government, at least for tribes in the United States, that represent the tribes. I understand what you're talking about in regards to community disputes, but I think that is up to the tribe to offer to tell you how they want you, how and if they want an outside entity to engage the community. And I mean, when you're talking about the change in tribal governments. Yeah, but is that so different from the change in any government, right? I mean, we deal with federal and local, the industry deals with federal and local governments that may also change pretty dramatically and relatively quickly. So I don't know that like the change, and I agree with you, tribal politics, like all politics, are subject to change in policy and direction, and that makes that harder. But I think the industry has experience dealing with those types of changes in other types of governmental settings as well.
So here's the last presentation. Mr. Iozsef Miskolczi. Iozsef is a senior consultant at SRK, and he will be presenting accounting for complexity in drain down monitoring, modeling for heap leach closure.
Right, we're almost there, folks. So no doomsday button. Yeah. Oops, I already pressed the button. So that's the title. That's the first page. Let's go to the stuff that matters. We're short of time here. So heap leach 101. I guess I don't have to remind anybody about heap leach in this crowd. This is more towards myself, actually, because I'm not a heap leaching guy. My interest is in the unsaturated flow. So what I'm going to talk about is really the very end, when all the gold has been extracted, all the economic value of the heap has been used up. And so now we are left with a bunch of solution that keeps coming at us. And so what to do with it and how to predict how long we are going to have this solution coming at us, and equally importantly, how much of it. So, in this picture, everything that happens outside of the heap, I will not touch because it's really not my area of expertise. However, looking at the heap itself, in this picture, it's a really nice frustum. Oh, I really love this word, frustum. Very nice and regular. In reality, most of the heap leach operations, the heap leach piles, do not look like this. Also, there's a lot of complications that happen in terms of, I swear I didn't touch it. But good pointer. Keep on. So, sorry, I'm lost in my own notes here. So to talk about the concepts of drain down. We define drain down for the purposes of this discussion as the very final chapter of the life of a heap, of the heap leach operation, of the heap itself. As the figure indicates, we have a flow that comes at us fast and furious in the beginning. It drops off relatively quickly, but then it takes a long time to get to some level that can be managed by passive matters, by passive water management solutions. I guess it is clear from many presentations that we had earlier today and about the fact that the heap leach is an unsaturated flow problem. We use Richard's equation to solve that. And typically, we need to know the hydraulic properties of the materials to be able to solve the Richard's equation and then further to predict the parameters that we're interested in. Right. And also, one needs to remember always that the moisture content in the heap leach at the drain down time, it's continuously changing and it's hopefully changing in one direction only. Wrong direction. So the important, why do we need to know this? Why do we want to know? Why do we want to quantify the heap leach drain down? Is because, well, as I said, we are. It's come down to cost, right? Like most things in mining, it comes down to cost. It's important to know the drain on flux and the timing of that flux, how long, the duration of the fluxes, of the various levels of flux, if you wish. So that ultimately we can design water management schemes that can take us from the active, in this case we talk about the active water management as pumping, and to a passive water management, which could be no pumping, or in some instances there's like sort of a semi-active where you need to do some water treatment, but you don't need to recirculate. And ultimately, design some optimal water management schemes, enclosure, and we get to the cost part of it. Oops, wrong way again. So the challenges with predicting this drain down are many. Again, many other presentations have dealt with different parts of these challenges. To summarize them here, essentially there's like, the hydraulic properties. The hydraulic properties are something that we ought to know by the time that we're closing the pile, but the reality is that sometimes we don't know enough of them, or we don't know the right ones. Then the geometry, it's complicated in many instances. For example, for my example, you're going to see one of the example is a little bit more complex system, on-off pads, they're really easy. Well, once it's off, it's off. But regular shaped frustums, less complicated. But in many instances, heap leach operations are belly fill. So in that case, geometry is quite complicated. Also, it's built in different lifts, it's built in different phases. The heap leach pile is expanded because very few of them actually look like what is being designed originally. Then material heterogeneity. Well, that's a biggie, because this brings with it, feedback loop, if you wish, to back to the hydraulic properties and also the geometry part of it, and quantifying the heterogeneity based on all these other parameters. You know, it's one of the most complex problems that we're having. Then, you know, operational history, that's one of the big challenges we're having because of the cyclical operation. You know, the various phases get irrigated, then a new layer is put on top and irrigated again, and all these things will influence the inventory of the solution that we have in the pile that we need to deal with at closure. And then final calibration. Calibration is an interesting animal. Typically, you know, I'm a consultant, so when we get to talk to the clients, they say, oh, we have years and years of data, and then they give us the data, and sure enough, there's lots of data, but unfortunately, few of the data points are suitable to calibrate for what we need to calibrate for. Also, you know, the operational data doesn't age well. A heap leach, you know, that the operational data of a heap leach from, you know, 3 years ago, it's going to be very different than what it is today, because more ore was added. There's, you know, the material, the physical and chemical changes that happen in the ore itself, you know, change the hydraulic properties ultimately, and so we're back to, you know, trying to calibrate the best we can, but you know, any data is better than none. So there we go. So for state of practice, you know, state of practice in drain down prediction. Well, the reality is there's no best practice as far as I can tell. There are many different methods to essentially to match the desired level of information. Starting from the very simple, the most simple ones, I guess many of you are familiar with the Hildy model. It's essentially a rectangular box of ore. You know, you have an operational moisture content, and then you turn off the irrigation, and there is a drain down curve, and you apply that, and what happens. And all the way to the more sophisticated ones. You know, the computational fluid dynamics models, you know, MATSIM, and there are, you know, we've seen two presenters in the show here that do exactly that, you know, trying to model the heap leach facilities. And that includes, you know, the physical and the chemical properties that are being modeled. In any event, so as I said, you know, these models range, they have a wide range, and from very simple to very complex ones. Arguably, the multidimensional, you know, three-dimensional models that capture the geometry and the heterogeneity of materials in an unsaturated, you know, coupled with unsaturated flow. They're a superior approach, but one should not forget that all models are wrong, but some models are useful. And therefore, you know, again, creating a model that's fit for purpose is, I think it's important. So the modeling approach that we followed for this particular talk, you know, we put this together and we used it for a number of heap leach operations. It reflects a little bit more complex situation, valley fill heap leach. And we used the building block approach, where we took each of the individual zones. Where's the green button? So each of these zones, as you can see, there are different phases. They were built, you know, from the bottom of the valley up. And so we quantified each of those with the various input parameters, and then essentially we assembled them into a unified model that accounts for some of the complexity. As you will see in my next few slides, some simplifications had to be made For example, we are assuming that all flow is vertical. We know that's not necessarily true. You know, we didn't account for any perched water tables or any of that complexity. And so so model inputs, you know, as I said earlier, essentially we try to quantify it, all the challenging parameters, if you wish. So we created our own drain down curves based on material properties, and we ran unsaturated flow modeling in Hydrology. And we calibrated those. We got some data for calibration, was good enough. Then, you know, the drain anchors are essentially a unit. Drain anchors, they were calculated for a square meter by square, 1 square meter, a meter by a meter column, which we then apply onto the geometry of the heap. The geometry was quantified, if you wish, by creating an isopack with the ore. The heap itself was broken up, if you wish, into areas of relatively equal heights. And so we back calculated then the surface areas, and then we applied a unit drain down curve to those surface areas. And that's how we calculate the initial moisture content, the initial inventory rather. The operational history in this case was introduced into the model through an irrigation schedule. And this irrigation schedule is actually what adds the time component to the model. And and then finally we added the climate, the precipitation and potential evaporation. As you can imagine, you know, in many areas, potential evaporation is extremely important because it's one of the mechanisms, in some cases, the main mechanisms by which we lose inventory. It is one of the convenient mechanisms because nothing needs to be done other than letting the water evaporate. Precipitation, you know, in some instances we have snowfall. You know, we had a little module that adds that can compute sublimation, for example. You know, high Andes zones, sublimation is important. And then past that, you know, we created a few quick closure scenarios. There's like a base case scenario, and then, you know, this is a fictitious case for this presentation. We had a base case, and then we quickly ran 5 other scenarios to sort of quantify the effects of the various elements, whether we put them on, you know, or into the model or not. And as you can see here, you know, the model essentially is telling us, oops, this is fictitious, but we actually ran the models. There's like anywhere from 2 years to 4.5 years for the transition to the passive water management. In this case, we defined transition to passive water management as a maximum flux that comes at us and can be managed in the existing ponds. Come on. Oh, work with me. Oops. Okay. The conceptual flow model, essentially, you know, we treated the heap leach as if it was two different areas, a passive drain down area and an active irrigation area. Recirculation, whenever recirculation was used, is always recirculated the same area. And then past that, you know, the passive drain down can happen separately, and the input from the passive drain down essentially becomes, or the output rather, becomes an input into the recirculation. Essentially, you know, the calculating these 2 areas separately allowed us to have a better control and, you know, better keep track of the inventory. And then also, you know, allowed us to break this up into different components that would allow us then to make to have an opinion on the water management, ponds and recirculation, surface evaporation, you know, enhanced evaporation, what the effect to that is. And so how it works, as I said earlier, we had unit drain down rates that we applied to a surface area that we quantified in the ISOPAC. And the final irrigation and the drain on schedule essentially becomes very important because it determines the initial solution inventory in the model. It does matter, so in this complex case, which phase was irrigated last, it does matter. It matters tremendously for various reasons. Specifically, the height. Essentially, when everything else is equal, the height of the irrigated area essentially will make a difference. Obviously, it's the higher the area, the more inventory you have, longer comes at you, higher fluxes. And then ultimately, precipitation and enhanced evaporation are accounted for separately, as I said, and so we have a better control on turning them on and off. So this is what the output looks like. As you can see here, there's no unit on the y-axis. This is not an emission. Well, it is an emission. It's on purpose, so to speak, because the curves, they have mixed units. The ones up here, they're all volumes, right? These are all inventory. As how the inventory changes, these green curves, it's how the inventory changes in time versus these curves down here, which are actually fluxes, which is, it's slightly different. What matters here is the interplay between between the different curves, and essentially what brings it all together is the time. It is the time series. And so the important thing is, as I was saying, we set ourselves a target for transition to passive water management, and that target is this little intersection here. Whereas like this purple dotted line is the pond capacity, the total capacity of the ponds on site. And essentially, for this fictitious scenario, we decided that the point of transition is where the inventory is equal to or lower than what can be stored in the ponds. And so, various scenarios can be run very quickly, and then one, can look at the interplay between these things. For example, you can see the enhanced evaporation, how that affects the fluxes, and then we have the active drainage. The active drainage is in this case we do have recirculation. So year over year we turn on the evaporators, how the fluxes change because we have less inventory in the ponds because of higher evaporation. All those interdependencies they can be assessed, and so pretty quickly one can assess can do some comparisons between a number of scenarios. And this is essentially a zoom in, if you wish, of the previous one where we only have the fluxes. And same thing, this is different scenario, obviously, but as you can see, the total evaporation changes seasonally because of we introduced this as enhanced evaporation only happening in the summer, for example, and how that affects the inventory. And essentially, at some point, we decide, okay, I had enough of this. Now I can transition to my passive water management, and how that changes. How very quickly you can see that the inventory and the drain on volume, essentially, that's the inventory in here, changes very quickly. And remember, this is one area of the big one, so it could be a little bit misleading if we are looking into comparing this to the big picture. This is this is the all of them as opposed to just the one small area. Okay, work with me. Okay, so essentially, we have confidence in our approach. There's nothing new under the sun. When I wrote the paper, the reviewer said, "Oh well, I've done this. Last century, I've done something similar. We used Lotus 1 through 3 to do that, but essentially, these models get created by people. Again, remember the fit for purpose concept, and so this is just our approach, the way we did it. The important thing to remember here, perhaps, is that this is a very simple, relatively simple model. We did a number of simplifications. We tried to introduce as many inputs as we could, and still keep it in Excel. And this was a wish of one of our clients that said, I want our site guys to be able to run the scenarios themselves, give us a platform that can do that. So Excel is that platform. Everybody's familiar with Excel. And perhaps equally important, there's no fudge factor in here. There's simple arithmetics. We took all the inputs, we calculated all the math, we applied the drain-on curves. We did the best we could with the drain-on curves themselves. We have a pretty good body of knowledge, I guess, to quantify, unsaturated flow that was applied here. And so there's no black box modeling that's happening. Although, with the advances that we have now in computing power, I guess we could slowly transition to machine learning, which is a black box, if you wish, with sufficient calibration. But again, calibration is going to be the critical element here to allow us to do that. And oops, thank you. Any questions? Where's the microphone?
What I wasn't clear on is how the analytical model, which I guess that's the Excel model,
Yes.
how that's linked to the numerical Hydrus model.
So essentially, the Hydrus model, the output from the Hydrus model, right, is a curve. Essentially, it's just like any other, Hildy uses, Brooks and Corey, I believe. And so we took for the different heights. So when we created the ISOPAC, we decided that in this particular case, for the one that I'm showing here, the figures for the lifts are 13 meters high. So we decided that we're going to run Hydrus curves for every 13 meter, so 13, 26, 39, and then on until the maximum height. And so that was created as a unit drain-down curve, right, for 1 square meter. And then we take that unit drain-down curve. We have the flux versus time. We take that unit drain-down curve, and then we multiply that by the surface area that is representing that particular height, right, of that particular zone, right, in the heap leach. And there's many different zones. There's 10 of them in this case. So it's like something like 80 odd columns that we had to calculate that way.
But in the case of one of your schematics, you were showing recirculation.
Yes.
And so in that case, then you decouple the drain down from the
That is correct.
recirculation. So there is a component of that recirculation that's infiltrating the heap leach pad.
Yes.
And will become drained down.
Yes. So perhaps I misunderstood your question a little bit. The time is essentially what is the common denominator here. And we created the drain down curves, and we said, at the operational moisture content, you start there, and this is when your drain down starts, and this is the curve. It is what it is. And then, excuse me. Then based on the irrigation schedule that we had in there, which said, area 3, for example, right? It's been last irrigated 9 months ago, for example. Then we go to the drain down curve and say, okay, well, on this day, for this area 3, you're on drain down curve number on day 0 plus 9 months. So we didn't start at the top, right? We start somewhere down the curve. And you do that for every single one of those areas, and then you assemble it all together into one number. But essentially, you follow the time that is required, or not required, rather, you follow the time that is dictated by your irrigation schedule back into, before your day 0 in the modeling. And that essentially allows you to calculate the initial inventory. I don't know if that's correct. I'm
Well,
happy to discuss
Yeah,
further
maybe
with you. Yes.
we can discuss.
Yes.
Yeah.
I think, I like little schematics. Sorry, arm waving is good, but little schematics I think help.
Another question?
How do you account for degradation of the ore in the long term in taking account of this? Because
Well,
it will affect
yes.
your drain down times tremendously.
That is a very, very good question. And the answer is we don't. That's one of the simplifications that we had to make. We created the drain down curves, assuming a property that doesn't change. We know the properties change in time, but for the drain down specifically, right, your time horizon is sort of defined somewhat, I guess, if you wish. And we say, sometime in the future, this thing is going to happen. And what do you think the properties will be at that point? Now that's in itself, it requires a different presentation, and it's a science in itself, an art, if you wish. But for this particular endeavor here, we just had to make the simplification that this doesn't change in time, because we couldn't quantify the changes in a way that makes sense in Excel.
Okay, let's say I'm an operator and you've given me this drain down time, it's 4.5 years. How do I know that's right and I can turn off the sprinklers? Like,
Well-
how do you field verify that? How do you know for sure that you're drained down enough, that you don't have enough inventory that's going to overflow your ponds?
Well, that's a very, very good question. And typically you don't. That's where calibration comes into play. And how does it happen today? Like, people sit and watch and say, oh, well, I've done this. I'm, 130 years old and I've done this 60 odd times. And I know it's going to take anywhere between 2 and 4 years. So, put aside some money and we'll see what happens. This is not going to get us to the very week that we need to get. I don't think that's reasonable to expect, but it's going to give us a good enough indication, I think. And perhaps the maximum value from this model is comparing the different scenarios and, applying a cover, not applying a cover. When you put the cover on, do you need to build a new pond? Is it cheaper to build a new pond? Is it cheaper to treat the water? Is it cheaper to put evaporators? Can you evaporate sufficient? So all those questions that come into, it's an art more than a science. And so right now, today, again, it's based on the operator's experience and the operator's ability to imagine the future. And so, we're slowly getting to the point where we can perhaps get closer to the truth, but I guess recalibrating from time to time would give us, better confidence, predictions.
Any other questions?
So with all at least 2 or maybe more important questions and the things that are left because they're because we don't have any answer or how to model that. Then the question arises, okay, so with all these things, simplifications and things left out, how much confidence do I have even in a comparative study for different situations? One starts looking with a little bit of pessimism in that how will the thing that he mentioned or he mentioned, we didn't consider that, neglecting that, or if we had means to include that, how much would that affect the comparative study with the model?
That's a very good question, and I can only answer by saying, all models are wrong. Some models are useful. It depends on what the answer needs to be, and as with all models, recalibrating from time to time helps us get closer to the truth. The reality is, these are just models. Yes, sir. Last one, I guess. I'm good. We can talk later.
So related to the unanswered question, is there any kind of instrumentation that you can suggest to get installed to monitor, let's say for the 4 years or whatever, the water levels or something, so you can, on the go, recalibrate your model and predictions?
So for this particular type of model, right, the only calibration you need is essentially drain down, right? Once everything else stops, when all the complications with adding new ore, re-wetting new ore, recirculating, not recirculating, enhanced evaporation, all those things, when all those go away, or at least you have a good handle on what is happening, they are cyclical and you're predictable, then you can look again at the drain down data and the actual data in the drain down period. And then, that sort of allows you to reposition yourself, if you wish, on the drain down curve. Now, the drain down curve, the shape of it may or may not be, it's usually not perfect, but I think, again, we have a good enough handle on the unsaturated flow modeling if we have good data. Now, coming back to the instrumentation, 2019, I believe, tailings and mine waste. There was a lady from Golder, Kelly, forgot her last name, and she presented a paper where they instrumented the heap leach facility, the whole thing, and they observed all the perch water tables and the traffic layers and all those things. So that is all possible, and so they made opinions on on the inventory and the flow that's happening through that heap leach. So that is possible. Earlier today, right, we talked about instrumentation that would survive the imperatives of dumping a whole bunch of rock on top of it. It is uncommon right now to have that instrumentation. It costs a lot of money. It's typically not done, or if it is done, it's like we've seen for the Golder paper in 2019. It's the exception rather than the rule. Going forward, certainly we can imagine all sorts of schemes of instrumenting this thing. But again, as I said, the most important thing is actually measuring what's coming out the pipe and having confidence in what's coming down the pipe in the drain down situation. In many, speaking to some of the clients, they ask them, well, how do you know, what's your drain down? What's your flux coming out of the heap? They are like, well, we monitor the levels in the pond. Okay, that's okay, but it's not good enough for what I need, the answers that I need. So there are improvements that we can make there. I don't know if that satisfies the answers. We can speak at large if you want.
Thanks for attending session 4. Enjoy the conference.